All right, everybody, here's 4.3. 4.3, sort of a standalone section, fits nicely right between the two major ideas that we cover in Chapter 4. And we'll see how it relates a little bit to what we've been doing with graphs. 4.3 is L'Hopital's rule. French guy, L'Hopital, is one of these people, a French noble back in the 1700s when calculus was first being spread across Europe. And he made some nice contributions. Turns out L'Hopital, just a little bit of history, L'Hopital wrote the first calculus textbook that went through all of continental Europe. He definitely left his footprint. People in Britain, they did things a little bit differently than the continental Europe at that time. A lot of rivalries there. Anyway, here's L'Hopital's rule, and there you see the pronunciation, L'Hopital. Over the O, there's kind of that, I don't know what that symbol is called. That's that little kind of a caret symbol. Yes, okay, there you go. L'Hopital. So what's the rule? So it turns out the rule involves limits. So we're going to learn how to perform limits that we would have been unable to do back in chapter 2 when we first learned limits. Turns out L'Hopital's rule is a way to go about interesting limits using derivatives. So it's definitely a derivatives application in the sense that it helps us figure out new and different limits. I want to show you guys a couple of examples of the types of limits we're going to be looking at. And these look interesting and definitely not anything we could have done back in that first chapter. So here we go. For example, let's take a look at this first one. The limit as x approaches infinity, e to the 3x over x plus 1. Okay, and you think, well, what's so interesting about that? Maybe the infinity is kind of interesting, but we covered those things. Okay, well, let's think about it. As x goes to infinity, what's going to happen with the numerator and what's going to happen with the denominator? Let's see, as x gets bigger and bigger, then that exponent gets larger, and e raised to a very big number, we would say if we just look at the numerator, that's going to infinity. How about the denominator? Well, x plus 1, as x gets bigger, that goes to infinity as well. And so we end up with infinity over infinity. And you might think that we know the answer, that we can maybe simplify that. No, 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 no. Okay, so here's the thing. When it comes to infinities, what's very important to understand is these are limits. These numbers are approaching infinity. Okay, of course, they never actually get there. And what's important is how fast do they approach infinity. Okay, it turns out not all infinities are made equal. Some infinities are actually bigger than other infinities. All right, so that takes a moment to kind of wrap your head around how can some infinities be bigger than other infinities? Because we're thinking about the speed at which those numbers approach infinity. Okay, so for now, I'm just going to tell you we do not know the answer to this. Infinity over infinity. It depends on the functions and it depends on some nuances. At this point, we don't know how to answer that. Of course, we're going to find out how in this section. Okay, and then my second example here, we've got a limit as x approaches 0 from the right. And okay, we have 2x over the natural log of 1 plus 10x. So as we normally would, we're going to attempt to just plug in the 0. That would be nice, right? So, okay, well, this would be 2 times 0, and underneath that would be the natural log of 1 plus 10 times 0. What would that give us? Well, 0 on the top, obviously. And on the bottom, we'd have the natural log of 1, and if you recall, the natural log of 1 equals 0 as well. So we get kind of a similar situation, right? Infinity over infinity. This time, though, it's 0 over 0. Again, you might be tempted to say, I know the answer to 0 over 0, right? They cancel out or something. Okay, no, 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 no. It's kind of like infinity. These numbers are approaching 0. And not all functions approach zero in the same way or at the same rate, you might say. Like here, it depends on which one approaches zero faster. That will give us an answer. Just like here, it depends on which one approaches infinity faster. So at the moment, we just say, I have no idea what that equals. It's going to depend on the individual functions involved. By the way, the sun's kind of peeking out from behind a cloud. Sorry for the shadows here. Let's continue. All right, we're going to do both of these examples as the section goes on. But first, obviously, I need to tell you what L'Hopital's rule is. It stems from this idea of the indeterminate form. We just witnessed both types of indeterminate forms. If a limit results in either 0 over 0 or infinity over infinity, it is said to be an indeterminate form and the value is unknown. Indeterminate, obviously, meaning we don't know how to determine the value. So what's kind of nifty, L'Hopital has this rule. Thank you very much. Specifically for indeterminate forms. So L'Hopital's rule says, for indeterminate forms, if you end up with either of these situations, 0 over 0 or infinity over infinity, here's what you can do. The limit as x approaches a of f of x over g of x, which is what we had, right? It was always, we had these fractions, right? Top and bottom, top and bottom. We can say, hey, keep the limit the same, but look at the derivatives. The derivative of f of x over the derivative of g of x. So again, we're thinking of the numerator and denominator separately, saying, okay, what is this derivative and what is that derivative? Let's compare derivatives, and it turns out those limits are equal. Now, obviously, I'm not going to go into all of the mathematical details of why this is true, but I think I can give you hopefully a good enough idea of why it's true with just this quick explanation. What are we doing in the first case when we take a function divided by another function? We are comparing y values. Think of that as a ratio of y values. For each x I plug in, I get this y value in a ratio with this y value. And sometimes, when we have an indeterminate form, we're not able to figure out what that equals. In the other cases we can, right? All the limits that we did that had fractions back in chapter 2, no problem. There were methods. But these examples we're seeing now, none of that's going to work, right? So what do we do instead? We say, hey, instead of comparing the y values, let's compare the rates of change. F prime of x over g prime of x is the ratio of the rates of change. Why is that? How can we get away with that when it comes to indeterminate forms? Because it's all about how fast they approach infinity or 0. The rate of change, right? That's the speed. Think of the infinity over infinity. How fast is that top function approaching infinity compared to how fast that bottom function approaches infinity? And turns out whichever one gets to infinity faster, it's like it wins this tug of war, and we can figure out an answer. Kind of those two infinities are pulling in opposite directions. Same way with the zeros. If maybe both of these were headed towards 0, but the speed is then critical. Which one gets to 0 faster? The top or the bottom? If we can figure out which one gets to 0 faster, then it's like that side wins the tug of war, and we can get an answer to the limit. Okay, so obviously we're going to do that sort of thing right now. Let's take a look. Okay, example. Show the limit is indeterminate, so we're going to begin by doing that. By the way, we need to show a limit is indeterminate because that's the only time L'Hopital's rule applies, right? So right? It said that right here. For indeterminate forms, only in these situations can we compare the ratio of rates of change. We didn't have that previously, so we didn't need L'Hopital's rule. Also, we want to be careful. L'Hopital's rule doesn't necessarily apply to everything, every limit out there, only to indeterminate forms. Okay, so first thing we want to do is show that this limit is indeterminate, and then once we know it is, then we can apply L'Hopital's rule, find the limit. Okay, so let's take a look. Our first example, x approaches infinity, e to the 3x over x plus 1. Well, we already talked through it. Yes, this is infinity over infinity. So I'm just going to say check. That's an indeterminate form, and we can proceed. From here, let's take a look. I've got the first line already presented, but we'll kind of talk through it. So what I'm going to do, I'm going to say, okay, let's start from the top. So I'm just going to repeat this part. Limit as x approaches infinity, e to the 3x over x plus 1. And now we're going to apply the rule. And you notice over here, I repeat that limit as x approaches infinity. I take a derivative of e to the 3x. Remember to use a chain rule there, e to the 3x times 3 over, and then I look at my denominator separately. The derivative of x plus 1 is simply 1, and there I have performed L'Hopital's rule, and of course we're going to go from here. But that's the rule. Okay, and you probably noticed something else that I haven't mentioned. When we write the equal sign, this is bizarre, and I've never seen this for anything except L'Hopital's rule. When we write the equal sign, above the equal sign, strangely enough, you write an L apostrophe H. What? Like, why? Indicating that we just performed L'Hopital's rule. Now, you may be thinking, why would you do that? I mean, there's no other situation where you indicate at the equal sign the type of operation you just did. You just do it, and then they're equal, and everybody knows. Here's why we do it. Imagine this was not here. Okay. What if we simply wrote an equal sign as we would in any other case? Then somebody looking at your work might not be able to figure out what you did. Now, we know a derivative happened and a derivative happened because obviously we're talking about this. But someone else who's just reading your work might not pick up on that, and they'll be like, what just happened? Right? Because that was such a drastic change. And they might think like you miscopied something, right? And some derivatives are easier to catch than others, right? This derivative on the numerator is probably pretty easy to catch. The denominator, though, x plus 1 becomes a 1. They might think like you just miscopied something and you forgot the x plus, and you just wrote the 1. Like, they might not be able to follow your work. So what everybody decided to do for the last several hundred years was say, okay, whenever you do L'Hopital's rule, because we might not catch that's what you're doing, you're going to write an L apostrophe H above the equals, and then everybody knows, okay, derivative and a derivative, and it's the limit. All right. So, of course, you guys need to do that as well. Okay, where do we go from here? Well, let's clean this up just a little bit. And there's not much to do, right? We'll put the 3 in front, and it's over 1, so we don't need that. Okay, so we're simplifying. It's the limit as x approaches infinity of 3e to the 3x. And if we can now perform this limit, then we're good to go, and we can answer the question. And yes, of course, we can. As x approaches infinity, then e raised to a big number is infinity, and we multiply that by 3, and we still get infinity. Okay, so there we go. The answer to this is infinity. Notice, right, we didn't know who would win the tug of war. Would the numerator get to infinity faster? Or would the denominator get to infinity faster? And after we perform L'Hopital's rule and we compare the rates of change, we can see, oh, wow, the numerator goes to infinity much faster than the denominator does. The numerator wins the tug of war, and the final answer to this limit is simply infinity. In another case, you might be wondering, what would the answer be if the denominator had won, the quote tug of war? If the denominator goes to infinity faster, then this whole thing would equal 0. And of course, that would have come out in our work. But in this case, we got infinity because looking back, it was the numerator that got to infinity. And yeah, it makes sense, right? E to the 3x or even e to the x is increases much faster than this line, right? This exponential function shoots up really quickly compared to a line. So the numerator is headed towards infinity much faster than the denominator, and that shows in our work. Okay, I want to do one more example in this video. It's similar to part A. I'm just going to change one little piece. Let's say x approaches infinity, e to the 3x, but this time the denominator is x squared plus 1. Just a little change. Let's see how that will impact our work and the answer. Okay, is the numerator still going to win? I don't know. Now it's an exponential is being compared with a square. Okay, first things first though, let's make sure this is an indeterminate form. Is it? Okay, let's see. When I put the numerator, infinity into the numerator, yeah, we get infinity. And when we put it into the denominator, well, infinity squared plus 1. Okay, that's infinity, so check. That is an indeterminate form. That is critical. We have to confirm that. We have to verify it's indeterminate because that's the only times L'Hopital's rule applies. Okay, then from here, what do we do? Well, I'm going to write it over again. Starting from the top, the limit as x approaches infinity, e to the 3x over x squared plus 1. At my equal sign, I'll write L apostrophe h. Let's repeat that limit as x approaches infinity. And then we'll take derivatives. Well, just the same, derivative of e to the 3x, let's just go ahead and write it as 3e to the 3x. Derivative of x squared plus 1 is 2x, so there we go. Now, there's nothing to simplify here, right? There's nothing to write any differently. So at this point, we would attempt to plug in infinity again. So what's going to happen? Ooh, wow, this is interesting. If we try to plug in infinity at this point, well, we still get infinity on the top, right? And we still get infinity on the bottom. It's still indeterminate. We still don't have an answer. What are we going to do? Who says you only have to do a L'Hopital step once? Do L'Hopital again. Okay, it's like a brand new problem. We're going to say, all right, we're trying to take the limit as x approaches infinity for 3e to the 3x over 2x. It's indeterminate. That means we're going to perform L'Hopital a second time. No problem. Let's take another set of derivatives. 3e to the 3x. Well, with the chain rule, we'd multiply by a 3 again and end up with 9e to the 3x. Derivative of 2x is simply 2. And there we are. There's nothing really to simplify here. So with the simplifying non-existent or out of the way, we can say, all right, well, let's try to plug in infinity at this point. What's going to happen? Hey, we don't have any more x's in the denominator. Perfect. When I put in infinity, we get infinity on the top. It's simply divided by 2. Well, infinity divided by 2, you guessed it, it's infinity. And so in the end, the numerator still went to infinity faster. But now that denominator, right, it definitely got faster than x plus 1, but it still can't beat e to the 3x, and so we still get infinity as our final answer here. But kind of the important issue and why I mention it. You may have to perform L'Hopital's rule more than once. Each time after you perform the rule, after you simplify, then attempt to plug in that limit again and just see what happens. And at that point, maybe you have an answer and you're done, or maybe you're still indeterminate and you have to do it. Again. There you go. Okay, let's stop this video here. We got more examples coming up.